Welcome back, everyone. Hope you're doing well. We're continuing our discussion on matrices now. Last time we were talking about determinants as a very useful way to determine whenever you have a singular or non-invertible matrix, or whenever you are able to take something with row operations to turn it into its row echelon or reduced row echelon forms in order to determine what kind of determinant our matrix would have. We saw it in three different ways. That's going to be useful for us here in talking about the span of vectors in a vector space. So in particular, matrices are an example of a vector space. So we'll be trying to take some spans of matrices today. We'll talk about spanning sets, essentially the idea of a set that spans an entire vector space, maybe a subset, just a couple of elements that in some sense generates the vector space. And then we'll talk about linearly independent sets as well. The notion of linear independence, the idea of linear combinations equaling zero if and only if each of the coefficients for each of the little scalar parts of the sum in a linear combination, each of those equaling zero individually. Let's go ahead and jump on in, why don't we? Let's go ahead and see what we talk about when we talk about these linear combinations, like what we're talking about here. Now let's take a vector space and let's take a subset. Now, we're not talking about subspaces a lot here, although we will introduce those later on. Let's talk about a subset of things like V1 through Vn inside of V. And let's consider all the set of all linear combinations of these things. Now, although this subset may not be a subspace, if we consider the set of all linear combinations, we do get a subspace. Remember that we have a subspace test for this. We go through and we ask, is it empty? You'll know it's got all of the V1, V2, Vn. It's got all of those particular elements inside of the set of linear combinations. You can just set 1 and then 0 for everything else to get any particular element in a linear combination. Then the set L is also closed under addition if you have two things of this form, where you have coefficients for R1, R2, and Rn, so on. And then if you try and add two of those types together, then you just have to add the coefficients together. So that's exactly what ends up happening when you try and add things together, so you're closed under addition. And then finally, scalar multiplication, because these can just be any scalars inside of the real numbers for the coefficients for these vectors. You can also get that is closed under scalar multiplication, and hence by our subspace test, this is a subspace of V. By the way, this is the thing that is defined to be the span of a set S. We'll define it a slightly different way, though. We're going to define the span of a set S to be the smallest subspace of V that contains S. What we mean by smallest here is that first things first, the span of this set, which we're going to refer to as span S, is indeed a subspace. And if you had any other subspace such that it had these sorts of properties of containing all of these elements inside of your set S, then if you ever have this, then it also contains the span of S. That's what it means to be the smallest subspace. Anything else with this property, span of S is contained within it. That's what it means to be the smallest. So first things first, the span of any set is well defined. And this is an important question. Can you have two possible smallest subsets that work? Well, let's say that you had two smallest possible subsets. Well, they both contain the set S, the subset that you're working with. And so if you took the intersection of them, it would also contain the set S. And you could also show that the intersection of two subspaces is itself a subspace. And because of this, you could get something smaller out of two smallest subspaces, the intersection of them. So that gives us what we are looking for, that this is a well-defined definition that we're working with. Now, effectively, what is it that the span is? Well, it is that thing that we were talking about before. It is the collection of linear combinations. Basically, if S is just a list of your vectors in your subset, then what you can do is put in front of any of those vectors any scalar multiple, any of these scalars, and just have it multiply times that vector. If you add all of those together, then what you get is the span of that set. Now, if S is infinite, something is a little bit interesting here, right? So let's say before we continue that we've been looking so far at examples where S is a finite collection of vectors. And now what's important here is that there are going to be some collections, some vector spaces that we look at where we need to consider spans of infinite sets instead. So let's take a look at what that might look like. If we're considering S to be an infinite set, then the span of S is a set of all linear combinations once you take finite subcollections of S. So see, you can see here, the sums here are all finite. We're not actually quite clear on how we would define an infinite sum yet for things like this. And so we just take finite subcollections from this infinite set and then associate with each of those the scalar multiple and allow those to add together. Now, this is any finite subcollection. So if you have infinitely many elements, you could take U1 through UK and then make a collection there. But whenever you make another element of your span, it could be a totally different collection of sets. It doesn't have to be the U1 through UK, the finite subcollection that you picked before. It could be a totally different finite subcollection with some or no intersection of the ones that you chose before. Now, if S is the empty set, you've got the nicest span ever. It's the span of the empty set is just the vector 0. Now, this is interesting because S was empty, so why does the span have anything in it? Well, what we're doing here is we're considering the empty sum, if you will. The sum with, when you're summing over nothing else, what you end up getting is just the 0 vector. That's all that you would have there. Now, let's go ahead and see some examples of subspaces, but this time let's see it in the world of matrices, 2 by 2 matrices to start. If you take the span of these two vectors or matrices, however you'd like to call them in this context, take a look at what these are. These are matrices that have a 1 somewhere on the diagonal and zeros everywhere else. And then you just keep going down the diagonal. If you take the span of everything on this form, you get what is known as a subspace of diagonal matrices. Diagonal because the only place where these can be non-zero is on the diagonal. And in fact, you can get any element on the diagonal that you would like. You just have to multiply, if you want it in the top left corner, you just have to multiply your first spanning element by A. And then you have to multiply your second spanning element by B. That gives you whatever you want in the bottom right corner. So that gets you any diagonal matrix that you would like in this space. The span of these sorts of elements, take a look at what these are. This is taking the diagonal matrices, but adding another element to it. This one is 0, 1, 1, 0. This is the one that has ones on the off diagonal, but notice the difference here. It's not 0, 1, 0, 0. It's 0, 1, 1, 0. Essentially, the things on the off diagonals have to be of the same element whenever I take their span. You can see that happening here. Essentially, when I have a scalar multiple C times this matrix, I'm going to get ACCB as my most general possible matrix there. These are all symmetric matrices. Symmetric matrices means that if you were to take the columns, switch them with the rows, switch them with the columns, essentially take the transpose of this matrix, then what you get is the exact same thing. Symmetric means that you can switch rows and columns and rows, take the transpose of that matrix, and get the same matrix back. So this is another example of a span set. Now let's go ahead and take a look at another spanning set here. The span of 0, -1, 1, 0, just of this single element. This is the subspace of anti-symmetric matrices. Okay, so this is all of those where A transpose equals -A. Notice we don't have anything on the diagonal here. And the reason that we can't have anything on the diagonal is that when I take the transpose, whatever this matrix is, anything inside of the subspace of anti-symmetric matrices, the things on the diagonal stay in the same place, right? So for example, when I take the transpose of something like this, everything here is going to stay in the same space. So why isn't this anti-symmetric? Well, notice that you have to then, in order for this to be anti-symmetric, take a negative of this matrix over here in order for this to be anti-symmetric. But this is not true. The only thing that is the negative of itself is 0. That's why 0 is the only thing allowed to be on the diagonal of these anti-symmetric matrices. So this is why matrices like this are not inside of this span. But you do see them return in the span of upper triangular matrices, for example, because now you can allow anything to be on the diagonal. So you have the diagonal matrices in there together with 0, 1, 0, 0, because that allows you to put anything that you would like in the upper right corner. That remains an upper triangular matrix. Finally, we have the span of 4 of elements with a 1 in each of the spaces in the 2 by 2 matrix form. And if you have the span of these 4 matrices, then this is just the entire space. This is all 2 by 2 matrices. All of them can be formed in this way because we know that all matrices take this form. You can just associate for the first spanning matrix its first scalar, second scalar, third, fourth, so on. And then You just add them all together and you can get this matrix however you would like. Let's define what a spanning set is. I have kind of mentioned it a couple of times. Let's talk about what a spanning set is for a vector space. Now, when we associate it to a vector space, we say that a spanning set or a subset is a spanning set whenever the span of that element is actually the entire space. That means for any element inside of our vector space, we can write the vector space as a linear combination of the elements inside of our subset S. So here's an example real quick, just to kind of get us an idea. Let's take a look at R cubed. So we're looking at the x, y, z coordinates. Here we have three vectors that form a spanning set for R cubed. Here they are, E1, E2, E3. This is 1, 0, 0. So this is a 1 in the x coordinate and 0 is elsewhere. E2 is 0, 1, 0, 1 in the y coordinate, 0 is elsewhere. And E3, 1 in the z coordinate, 0's elsewhere. If you span all of these things together, then it turns out that you can go through and say, okay, if I want to take any coordinate, x, y, z, it's just x times the first element plus y times the second spanning element, and then z times the third spanning element for each of the x, y, and z spanning elements respectively. Right, so this is known as the standard generating set for R cubed. You'll hear me use the word generating every now and then, because what happens is that if you take the span of these more basic elements, then they generate the set X, Y, Z. There's also something to be said about them not being redundant. There's not too many elements inside of the generating set, although we'll talk about that later when we discuss linear independence. We also have that the 4 elements that we had for the spanning set of M22, that's a spanning set from the same discussion of what we had before. So this is just repeating that same discussion. This gives us the entire space of 2 by 2 matrices. Let's go ahead and define the span. So we've already talked about a little bit about this. We've said that the span is the smallest subspace that contains a set S. And in this case, it does not have to be the entire vector space. It's not a spanning set. It's just the span of the set. If S is not empty, then W consists of all linear combinations of this form. And you can see here that this is regardless of whether or not S is an infinite or finite subset. You can always just write it in this sort of form of just finite collections inside of your set together with scalar multiples for each of them. Okay, seeing that my screen has decided to stop. Give me a moment here. Okay, I think we're back. So we say that the set S spans the subspace W, or that the S is a spanning set for W. Notice that we use spanning set in a slightly different way because we talked about it in terms of the subspace W rather than for the vector space V. It doesn't have to be the entire vector space V. It can just be a spanning set for the subspace it generates for that of W. So just some terminology there. Now let's go ahead and get into the nitty-gritty with this and see some details. How could we find spans? How can we determine what is in a span? And this is a type of problem that it was good for us to explore for a little bit. And it's good for us to talk about this sort of problem and figure out whether or not a vector is inside the span of some other subset. Let's let our subset in this case be V1 and V2. Let's say that we're going to try and figure out what the span of V1 and V2 is. In particular, let's see if we can find enough to see if W, the vector W, is inside of it. Is it the case that if you have V1 is 1, 2, 0, V2 is 3, 1, 1, you can see that these are both coordinates in R3. And let's let W be 4, negative 7, 3. Let's determine if W belongs to the span of V1 and V2. Now, in order for it to do this, it has to satisfy a system of equations. Here's that system of equations. See if you can see where this stuff comes from. Basically, we're saying that we can write this W as a linear combination of V1 and V2. So what we do is we break it apart. We break up V1 and V2 in terms of its X, Y, Z, and components respectively. If we do this, we get something like this, 4, negative 7, 3, writing this as a column vector here, equals R1 times the first vector, which is 1, 2, 0, plus R2 times the second vector, 3, 1, 1. Now, I have this written as a vector equation. But really, you can see here that there's three equations hiding inside. One of setting all the x components equal, one of setting all the y components equal, and one of setting all the z components equal. And that's exactly where the system of equations comes in. You can see that 4 equals r1 plus 3r2 comes from distributing in the r1 and the r2 into each of their vectors respectively. If you do this, you get the x equation, if you will. So this can be thought of as the x equation. And then you have the y and the z equations respectively following right underneath it. Now, this is a system of equations for which I can apply any number of means of solving. I could do Gauss-Jordan elimination, I can do substitution, I can do elimination. However I'd like to go through and do it, at the end of the day, I do get values for r1 and r2. r1 equals -5, r2 equals 3. Now, the reason that we wanted to find these numbers is that it turns out you can plug those in for our original equation that we had down here. Hence, W is -5v1 plus 3v2. So W is inside of the span of these two vectors. It can be written as a linear combination of these two things. And that's exactly what it means to be inside of the span. All right, so that's kind of how we can kind of get the ball rolling here. That's how we can get started. Let's go ahead and keep going here. And let's see if we can show that for R2, if we take these two vectors, V1 equals 2, 5, and V2 equals 1, 3, let's see if we can show that the set V1, V2 is a spanning set for R2. Recall, spanning set, again, means that any vector inside of R2 can be written as a linear combination of these two. So in this case, you're going to see that instead of us trying to say, okay, let's just take our favorite vector and let's just show that that's in the spanning set, we're going to let this be an arbitrary element of R2. This is important to show that any element in spanning set for R2 happens to be a linear combination. Then what we're trying to say is we don't get to choose what W is. W is some vector out there, and it has some x component and some y component. We'll just call it A and B respectively. And we want to show that there exist some scalar multiples of these two vectors such that when you add those corresponding vectors together, you get this generic variable, this AB. Well, in order for us to do that, we would need to be solving the same system of equations as before. We're setting the x is equal and the y is equal in order to figure this out. Let's see if we can go through and solve this. I'm starting to see that there is a matrix equation going on here. I have a coefficient matrix A times R1, R2 equals the vector AB. So there's a matrix equation going on here. Well, this gets us back to what we were just talking about in our determinant video, and a little bit in our subspace video too. We talked about having a coefficient matrix for a system of equations. And the way that we know that we can solve this system of equations is if and only if the matrix A is invertible. And so let's go through and see if we can form what that matrix is. We just take the coefficients of each of these variables once they're lined up neatly, and we get 2, 1, 5, 3 for that coefficient matrix. Well, is this matrix invertible? We just have to find out by taking the determinant. The determinant of that matrix is 1, which is not 0, which means that you can form a determinant for this, or an inverse for this. Since the matrix C is invertible, the system has a unique solution, thanks to our discussion from before. So that means that W can indeed, we can find the vectors or the scalars R1 and R2 that solve this matrix equation. That means that W is indeed in the span. And so we are done. A neat little way to kind of show back to what we were talking about for matrices before and how it connects to talking about the span right here. But there's more than one way to go through and show this. Another way to kind of show that this is a spanning set is to show that it has the standard generating elements for R2. You remember back in the R3 example, we said that for R3, 1, 0, 0, 0, 1, 0, and all that sort of stuff generates R3. Well, we can say the same thing about 1, 0, and 0, 1 in the case of R2. Each of these two vectors, once you take any linear combination of them, that is a known spanning set for R2. In fact, it's the standard generating set. You can form any xy by just taking x of the first standard as generating vector plus y of the second generating vector. Once you get all that put together, that gives you any vector you would like. So this is a standard spanning set. Well, what are we going to do with this? What if we showed that this span of V1 and V2 contained 1, 0 and also contained 0, 1? Well, if it contains 1, 0, then we can, of course, make any scalar multiple of 1, 0. If it contains 0, 1, we can make any scalar multiple of 0, 1, 2 by just multiplying the whole thing through once we figure out the original linear combination. And finally, we can add those together to get any particular element in R2 that we would like. So it turns out let's try and go through and see if we can just show that E1 and E2 belong to this span. Well, we've got a system of equations to go through and find. We go through and do that, and we do get solutions for R1 and R2 here. And then we do the same sort of system of equations for E2. You can see the only difference is that we're setting this one equal to 0, 1. And that's going to give us another setup here. Okay, so we have E1 is this, E2 is this, and these are both systems of or E1 and E2 are both linear combinations of vectors in V1 and V2. So for any vector W, what I could do is say, okay, well, if it's written as AB, I know that I can write this as a linear combination of E1 and E2 like I do right here. But E1 can itself be written as a linear combination of E1 and V2, as can E2. So we can just multiply everything out and get a linear combination for W in terms of V1 and V2 as well. Pretty interesting stuff. So note that because R2 was spanned by our standard generating set, that was why we were able to say, okay, let's go through and just check for these vectors, see if they belong to the span. So whenever E1 and E2 belong to the span of these two vectors, then hence the span of E1 and E2 belongs to these two vectors. We saw that with the vector W. You can just multiply E1 times A, E2 times B, and then distribute out. And then you get that E1 and E2's spanning set is inside of the span of V1 and V2. Well, in this case, the spanning set of these two generating vectors was all of our vector space. It was R2. That means R2 is contained within the span. Well, since any span of R2 vectors will be in R2, we get the opposite inclusion as far as sets are concerned as well. So these two things are equal. In general, is enough to show in order for the span of one set to equal the span of another set. And this is a good one right here. It's enough to show that if S1 is inside of the span of the second generating set of S2. So if S1 is inside of there, then we know that you can just take the span of S1, and you know that this will be inside of the span of S2. And then if you show the opposite, but this time only showing that the subset S2 is in the span of S1. Notice I don't have to show the span of S2 is in there, just S2, the generating set for the spanning set here. Then I know that from what we discussed above, that the span of S2 is also a subset of the span of S1. I have A as a subset of B is a subset of A, hence the two sets must be equal by double inclusion. So that's a neat little trick to show that the span of one set is equal to the span of the other set. And it's going to be very useful for us later on. Let's go ahead and see some more properties of the span while we're at it. Let's keep looking through subsets of a general vector space V. Let's say, for example, that one subset is a subset of the other. Let's say S naught, for example, this one is a subset of S. Well, if you have something like this, then what happens if I take their spans? Well, it kind of makes sense, right? You have that S naught is a subset of S, so we can take the spans of both of these. S naught is certainly, for example, going to be a subset of the span of S, because that's going to contain the set S. And hence we can take the span of the left-hand side and remain in the span as well, thanks to our discussion at the previous slide. So we know that we can basically take spans of both sides and get the same subset variation. Now, if the span of our subset is the vector space and this subset is a subset of S, then by the above principle, then we can just take the span of S to be the same vector space. That's because the span of S can only be bigger than the span of S naught, but the span of S naught is the entire vector space. Now, let's say that you take a collection that is a spanning set from my vector. And let's say that one of those vectors in that spanning set actually is a linear combination of the others. That means that you could find some sort of way to connect V1 through Vk, right? A V1 plus B V2, so on and so forth, adding all those together to equal the vector V0. Then it turns out that you have one vector too many. You remember how we said that you can have redundancy in a generating set? Here, V0 ends up being redundant. We don't really need it. We can take this straight out of our spanning set. This is good enough. It spans the exact same space because V0 was just a linear combination of V1 and Vk. Here's the idea of the proof. If V0 is this linear combination for everything here, then what you do is you say, okay, what you can do is take a look at any element inside of our vector space V, which, since this is a spanning set, V0 through Vk is, that is. Since this is a spanning set, there are some elements T0 through Tk that can be associated to them to give us that entire element. Then we can remove V naught entirely. Here's how we do it. We just substitute in what V naught is in terms of this right-hand side equation. And then we just combine everything together and we get coefficients for V1 through Vk, showing that this element was indeed in the spanning set of V1 through Vk. Since this was just a general element of V, then we're good to go. So same sort of deal. If we take this, if we have, it's kind of like the opposite sort of deal. If you have the span of a set unioned with a vector space, and you determine, by the way, that that's just the span of your original subset with you take this vector out, this V naught vector out, then it turns out that the only way that that can happen is if your V naught is actually an element of your spanning, of your original set S naught. So if you're adding an element to your span and realizing, oh, I'm just getting the same spanning set, then what that means is that that extra element you added was already in the span of your set. You didn't add anything extra. All right, so the way that we can kind of show this, we've already got one direction thanks to what we did up above. So if V naught is in the span of the other elements, then by what we did above, you can get this inclusion over here. And then on the other hand, you just have to show the other inclusion. If you add more elements, just like what we saw from above in our first bullet point here, if you add more elements, you get the span going the other direction. So just a neat little trick there to show that. This is all connecting to the big definition for this latter part of this. And we're going to try and connect everything together here with linear independence. Linear independence means that you don't have any redundancy in the subset that you've chosen, at least in terms of trying to take a span. That means that whenever you look at maybe the opposite of linear dependence or independence, if you look at linear dependence, that means that you can write some combination of these vectors and get all the way to the zero vector. You can get all the way to the zero vector. So for example, whenever your coefficients here, by the way, in order to get this, you have to have some sort of non-trivial element or non-trivial solution R1 through Rk such that this system of equations equals 0. If you don't get that though, if the only way that this is equal to 0 is if all of R1 through Rk, your coefficients for your linear combination, if all of those individually equal 0, then that's what we mean when we say that the vectors are linearly independent, that there is no redundancy in choosing spanning elements inside of there. So we say that a set of linearly dependent, or a set itself is linearly dependent if you can find linearly dependent vectors inside of it. Otherwise, you have a linearly independent set. So same sort of deal. We're just taking the S set S to be more than just a finite collection of vectors. It could be an infinite collection of vectors now, if we want it to be. That's what that last statement is helping us do. Before we continue on to talk about this connection between linear independence and span that helps guide our intuition, let's see some examples of linear independence here. Well, we've got our generating elements back again from R3. Here we have one that generates X, one that generates Y, one generates Z. Indeed, if you had each of these things coming together to try and equal the zero vector, we can see what happens here. E1 is the vector 1, 0, 0. So if you multiply it times X, you just get X, 0, 0. And that contributes to the X component and the X component only. E2 contributes to the Y component and the Y component only. Z to the Z component and the Z component only. Hence, if this were to equal 0, this equation here, then we would have an XYZ component, an XYZ vector that equals the 0 vector. But the only way you make that work is if you do the system of equations and you realize that you just have to set the X components equal. So X is 0, hence Y is 0 and Z is 0 as well for the same reasoning. That's exactly what we mean when we say there's this collection E1 through E3 is indeed linearly independent. We had the same thing with the matrices that we were looking at before, this kind of thing that spans the 2x2 square matrices. So E11, E12, E21, E22, these are all kind of labels that we can put to this sort of generating set. And you can notice that it's the same sort of deal really as R3. Here you have a 1 in the top left, a 1 in the top right, a 1 in the bottom left, a 1 in the bottom right. So if you ever try and get these to be equal to the 0 vector in this space, which by the way is the 0 matrix, sometimes just referred to as O, a capital O, which is what's given here. If you ever try to get these equal to the 0 vector, then what you get is a matrix where each individual entry must equal 0, but that is the definition of linear independence there. So a couple of definitions or a couple of examples to help guide our intuition there as well. But that's just for matrices and for Rn, Euclidean space. What about the functional spaces that we've been talking about a little bit? What about the polynomials? What about 1x, x squared, all the way up to x to the n? Okay, so what about this finite collection? Well, let's see what happens when you take a linear combination of each of these polynomials and try and get it equal to 0. Now, remember that this means 0 as like the 0 function. That's what this one is referring to. This means the 0 function. We aren't actually trying to solve for an x here. We're trying to figure out where is it that this linear combination of these polynomials, if you put them all together, is it equal to the 0 function? Well, you've seen polynomials. So you know that a lot of them, especially when they're non-trivial, end up going woo, 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 and stuff like this. And the only way for them to be 0 is if each individual coefficient for them is 0, including the constant coefficient, especially the constant coefficient. So that's the only way that we could make that work. So this means that these polynomials, 1x, x squared through xn, these are linearly independent elements of the space of functions on this f of r. Could you say this to be true about c of r? Yes, you could. Could you say it be true about p of r? The polynomials? Yes. These are all linearly independent sets, regardless of what functional space you're putting them in, as long as it's a valid functional space, namely one that the polynomials 1 through x to the n are already in. But we don't have to stop there. We could go ahead and look at the infinite set 1x, x squared, going to x to the n, and then also going beyond it, going to any power of x. This is an infinite collection now. This is a subset that is infinite inside of the space of fr. But you can also show that this is linearly independent. How do you do this? How do you show that this is linearly independent? Well, remember that the definition of linear independence allows you to take finite collections from this infinite set. Well, any finite collection of this infinite set is going to have a highest possible degree, some x to the n, if you will, of the x powers that you are choosing. Well, then you're just back into the first case. You have polynomials of this form, where you have certain coefficients that you can put in front of each of the powers of the polynomials you have chosen. The only way that that can be 0 is if each of those individually are 0. So that's just a small little difference in having an infinite set here. As something being linearly independent. You're getting to choose a finite collection before you continue. Let's go ahead and take a look at another finite collection while we're at it. Let's take a look at the polynomials P1, P2, and P3, all living inside the space of polynomials. Here, let's let P1 be just the constant polynomial 1, P2 be the degree 1 polynomial x minus 1, and then P3 be the degree 2 polynomial x minus 1 quantity squared. And the question is this going to be something that is linearly independent? Well, the only place that we know to start is to try and put coefficients in front of each of our generating elements. Notice we have a1 times 1 here for the first term, and then try and set those equal to 0. Well, maybe it would be helpful for me to try and get the constants all to be one term, the x terms all to be one term, and then the x squared terms all to be one term. And that's exactly what I have here on this last line that I have uncovered so far. So let's take a look now and see what happens if we try and solve this. We want this to be equal to the 0 function. So we want this to be equal to 0 plus 0x plus 0x squared. Well, what's the only way that this can happen? Only way that this can happen is if you take each of these individual constant terms, set them equal, x terms, set them equal, and x squared terms. And set them equal. You can see that's exactly what we have here in this line. We're taking each of those coefficients and setting them equal. Well, if a3 is 0, well, that shoots us in the foot for the x terms coefficients. That's a2 minus 2 times 0 now, so a2 has to be 0. Similarly, a1 must be 0 as we go through and solve that system of equations. Another example here is like looking at the real numbers versus the complex numbers. The numbers 1 and I, here again, I is the square root of -1, are linearly independent in C, regarded as a vector space over R, right? And this is how we usually think of our vector spaces here, right? We can think of complex numbers as being of the form A plus BI. This is kind of a linear combination, isn't it? You're taking a real number like 1, a times 1, taking its span, and then adding to that and working with the span also of the number I, the square root of -1. That's the b times I. So this is a linear combination of those two elements, 1 and I. Turns out that that's linearly independent. There's no way to get this equal to 0 unless both a and b equal 0. Also, the empty set is always linearly independent. The only way you get to be the 0 vector and the empty sum is if, well, there's no coefficients to choose, so you're always linearly independent in that collection. Let's go ahead and see, let's get to the nitty-gritty again and start seeing some problems with these vectors. Let's see if this collection is linearly independent inside of R3. Here we have V1 equals 1, 2, 0, V2 is 3, 1, 1, and V3 equals 4, -7, 3. So what we're basically trying to ask is, let's take a collection of, or let's take an arbitrary linear combination of this and set it equal to 0. The question is, are we forced to conclude that R1, R2, and R3 are 0? There's a reason I say that. I could just go ahead right now in order to solve this system of equations. I could just say R1, R2, R3 are all 0, and I get a solution. It's going to be the 0 vector. We know each individually is 0, and they add up to be 0. We're not looking for what is known as the trivial solution to this problem. We're looking for non-trivial solutions, ones where it is not the case that R1, R2, and 3 are all identically 0. Now, it's okay if one is 0, right, and the other two are non-zero, for example. Maybe they work against each other in that way. But it can't be the case that all 3 are 0. So that would be what we are calling a non-trivial solution. So let's see what we get. We've got to set the x's, y's, and z's equal to each other, just like before. And here's what we get whenever we try and set up that system of equations. Maybe now we can set up our augmented matrix and attempt to try and figure out what kind of values we can get for R1 and R2. Now we go through and we row reduce this matrix. And once we do that, we realize that these vectors are linearly dependent whenever this matrix is singular, or just whether the matrix over here is singular, or when you get a non-trivial solution to what this thing is. Essentially, what this would end up looking like is that once you go through and row reduce, you might have some things up here. Maybe this is a pivot column right here. And then what could happen is that you have a part of your matrix that has just zeros in one of the rows. That is going to correspond to a vector, or one of the R1, R2, R3s for us here, at least in the case of square matrices like we have right here, where one of the coefficients or one of the scalars that you're choosing can be anything. It's a free variable in terms of what that can be. In particular, if you have something where it comes out into this form, this will give you an ability to choose one of your vectors that is not a pivot column and make it a free variable, allow it to be something else. So in this case, when I go through and do this, indeed, I get that the determinant of A is equal to 0. Let's see, I don't think we talk about this anymore. When I went through and tried to solve this one, I said, okay, well, is there an actual concrete example that I could give? And the one that I was thinking of, I think, was that V1 can be written as, I think it was V3 minus 3V2, something like this. And so basically what that means is that if I add these vectors onto one side, then I get that this is a way to write everything here non-trivially as the 0 vector. You can go through, check my work, and make sure that looks okay. But I think that all should be at least something close to what we're looking for here. I think my 3 went in the wrong direction, perhaps. Either way, there is a way for us to go through and do this. I think I needed to put a coefficient in front of the V1, actually. That's my bad. So this is the general idea of what this sort of solution might look like. This one isn't quite a solution here, but this is an idea of what that sort of thing might be looking like. All right. Okay. So these are what we have for this system of equations. Okay, there we go. I fixed it. There is a -5 in front of the V1. Once you get that -5 there, this should work as a way of showing that there is linear dependence in between these vectors here. So let's keep going here and talking about this next theorem. How can I get linear dependence and basically the way of showing that you can write one of these vectors as a linear combination of the others? Well, we kind of saw it in just that previous example that we were working on. In that one, you was a way to write v1 or a scalar multiple of v1 in terms of the other two vectors. And once you move back and forth that one term, you get something that equals 0. This is exactly what that theorem is talking about, is that the linear dependence relation, all that does is it shows you can write one vector as a linear combination of the others. That's exactly how we're going to start here. Let's pick one of the vectors in this beginning linear dependence relationship in the 1 implies 2 direction. Let's pick one where something is not equal to 0. R sub I is not equal to 0. Now we know that there is some scalar multiple here that is not equal to 0 because we're starting by saying the vectors are linearly independent or linearly dependent. So there is a non-trivial solution here to this 0 vector. So we can ask for some R sub I to be not equal to 0. Well, what we're going to do is we're going to write all of the other vectors in terms of v sub I. And that's exactly what we do. The idea is you isolate that v sub I, subtract everything else, that's hence of the minus signs here, leaving the v sub I or R sub I times v sub I by itself minus everything else. And then you divide everything by R sub I. And that gives you this nice little formula here for writing v sub I as a linear combination of the other vectors. And we can also go back. If you have that vi can be written in this sort of scalar form, then what you can do is just subtract the vi. Nothing wrong with that. If you subtract vi here, that's what we do right here, then you get the linear dependence relation. You get all of these terms being added together to give us 0. So these two things go hand in hand. They are equivalent notions. Let's go ahead and see some more facts on linear independence while we keep going. You might see that there's a little bit of a reverse option going on here. So for example, you remember how we said if you have some set that spans a set and you like a bigger set, then that set also spans. Here, if you have a set S which is linearly independent and you have another set that is smaller inside of S naught, right, is a subset of S naught, then S naught is also linearly independent, kind of a reverse relationship. Do you see it? It's like if you had a spanning set and you made it bigger, it was still spanning. If you have a linearly independent set and you take a subset of it, then that is still linearly independent. Same sort of idea, if S naught is a subset of S and S naught is linearly dependent, that means that you can write one vector as a linear combination of the others, then so is S. S itself, the bigger set now, and that's because you can just take that same collection, that non-trivial solution that equals 0 inside of S naught and get to write one of those vectors as a linear combination of the others. So it's just the same sort of deal. Now, if S is linearly independent and V is a subspace of W, then the same equation holds inside of the bigger vector space, right? V and W here, W is meant to be a vector space itself. And so we're just saying that the same equation holds. If it's linearly independent, that is, right? You have the same collection of vectors inside of S. They just happen to live inside of V. The V is a subset of W. So it's the same sort of equation process. The definition reads the exact same, because what you're referring to are the vectors R1 through RK, or V1 through VK, I should say, inside of the vector V, which just happens to be a subspace of W. The empty set, linearly independent. It's winning on both sides. It's linearly independent here. In fact, any set containing 0, however, is linearly dependent. Well, why is that? Well, I can write a linear dependence relationship that equals 0 here for any collection of set that contains 0. And that's because 1 times the 0 vector, if 0 is inside of my set that I wish to show is linearly dependent, 1 times 0 is 0. That's a non-trivial solution to that equation. So that is a way to show you get a linear dependence relation from any set containing 0. Now, 2 vectors, let's say you just take 2 vectors, v1 and v2. That's your set. It's not any of the other elements, just those 2. These 2 vectors are linearly dependent. That is, you can write some relationship R1 V1 plus R2 V2. Whenever you get this only happens when one is a scalar multiple of the other, meaning you can write one as the other times a scalar multiple. And you can just change the variables around in this equation like we did in the previous slide to get to figure that out. Then 2 non-zero vectors V1 and V2 are linearly dependent if and only if either of them is a scalar multiple of the other. This one, the only thing I think that changes really is the idea of non-zero. It's just the same sort of idea here. So now, finally, let's go ahead and see if we can figure out start relating things from linear independence and span. So let's go ahead and see something that connects these two concepts together. If S naught is linearly independent, so you have an linearly independent set, and then you take some vector that's outside of the linearly independent set, then what you do is consider the set of you taking that spanning set or that linearly independent set and throw the vector inside there. Well, if you get this, then it turns out that this is a linearly independent set if and only if that V naught was not in the original span of your set S naught. Well, why is this true? This goes back to that same kind of analog definition of what we had before, this time in terms of span. If V naught were in the span of the set S naught, then adding this element here would introduce a linear dependence relationship. Because why? You're getting V naught is going to be a linear combination of the other vectors in some sort of way. On the other hand, if V naught is not in the span, then there's no way to introduce a linear dependence relationship because V naught was not in the span to begin with. Span literally means linear combination. And so hence you have to, since there's no linear dependence relationships in S naught to begin with, then adding V naught doesn't introduce any new linear dependence relationships. Now let's talk about a time when you are guaranteed to have a linear dependence relationship. Let's say you're working in the vector space Rn. And let's say that you have m vectors here. So you have v1 through vm. You can guarantee that these vectors are linearly dependent whenever m is greater than n. That is, you have more vectors than there are dimensions inside of Rn. Let's go ahead and prove that real quick. Well, we're going to go through and set this as a system of equations, try and figure out what this is. I'm going to get a coefficient matrix here, right? A is going to be A11 to AMM, and we've got to keep going, AN1, and this is A1M, things like this. And so we're going to get this little coefficient matrix here. But something unique is going to be happening with it. Do you notice that there are n equations because there are n coordinates in Rn? So this is an n row matrix where there are m columns. This is an n by m, and in particular, from our assumption, there are more columns than there are rows. Well, when I go through and try and do row echelon form, what's going to happen? I'm going to eventually run out of places to go ahead put pivots to put pivots or anything like this. So I'm either going to get like a system of equations that doesn't have a solution, which by the way is not possible because this is all equal to 0, and we know from our subspace slideshow that you can always just set all the T1 through Tm equal to 0 to get a solution here. But you're going to get that there is at most one solution here for this system of equations, and that's because you have more columns than you have rows. So pivoting is going to become an issue along the way. Namely, you're not going to get just a row of zeros in one way. The only way that you could do that is if you had a linear dependence relationship between V1 and Vm. So that's exactly what's being said here. The number of leading entries in the row echelon form is at most n. That's because there are n rows. However, if m is greater than n, then that means that the ones that are not pivot columns, those are free variables. Therefore, the 0 solution is not unique. So there is some sort of other way to go through and do this. So now we can see that there are ways to guarantee linear dependence here. And we're also starting to see a connection between a space itself and what it means to have a linearly independent set. We're going to connect these notions together in something called a basis, or when we define the dimension of a vector space later on. But for now, let's go ahead and keep talking about linear independence in this vector space of Rn, because like we just saw in the previous slide, we get to use this machinery of coefficient matrices for systems of equations. Let's see it here in Theorem 1. Given an n by m matrix here, again, we don't have to have number of columns is bigger than number of rows. This is just n by m matrix A. The following conditions are equivalent. First condition, columns of A are linearly independent. Okay, so what that means as vectors in Rn. So if I have, for example, 1, 0, 0, 2, then what I'm considering are the vectors 1, 0, and 0, 2. That's what it means for having condition 1. Condition 2 is, well, if they're linearly independent, that means I can't rewrite the column so that one is a scalar multiple of the other or a linear combination of the others. And in that case, the only solution to the matrix equation, ax equals 0, is going to be x equals 0. Pretty neat there. We know that, for example, whenever we're in condition 1, we can't have it be the case that m is greater than n, because then we'd have a linearly dependent collection of columns there. So x equals 0 is the only solution to this matrix equation. Then finally, the row echelon form of A has a leading entry in each column. Basically, you have it going all the way down doing the row echelon form. You don't have just a free variable sitting around somewhere. And then we can move on to theorem 2. Let's go ahead and talk about the place in which n and m are equal, because here we can go a little bit further. Given a square matrix A of the same dimensions, the following conditions are equivalent. Well, we're going to connect this back to the idea of invertibility inside of this system of equations. Well, we know that whenever you have a determinant of A is not equal to 0, you have this sort of unique solution inside of your space. Well, what is that going to mean? That everything has its own pivot column, and hence we're going to be able to connect back to theorem 1 and say columns of A are linearly independent. And we're connecting back through that thanks to 3 here. And then finally, because we can just take transposes and do the same process, we know the rows of A are linearly independent as well. That's neat because it's essentially we're saying that the column space and row space of this matrix respectively all are generated from linearly independent vectors that we know they come from the square matrix A. Let's keep talking a little bit about this notion of having more vectors than dimensions in our space. Let's look at R3, a 3-dimensional space, and let's consider 4 vectors inside of there. Well, we know automatically that there has to be some sort of linear dependence relationship here. Now, the question is, how are we going to find it? Where is it going to be? So let's see what we can do here. Let's take 2 vectors. Let's take the vectors, first of all, v1, 1, negative 1, 1, v2, 1, 0, 0, v3, 1, 1, 1, v4, 1, 2, 4. And let's see if we can find that linear dependence relationship. Well, maybe I could start by taking a look at pairs of these vectors. We know that any 2 vectors are linearly dependent whenever one is a scalar multiple of the other. But looking at v1 and v2, I see that there's no scalar multiple of one versus the other. No way to make that work. Hence, these 2 are linearly independent. Let's try and add in v3, though. What happens if I add in v3? Well, it turns out these are linearly independent as well. At least it is if and only if the matrix A is invertible. But if I go through and try and take its determinant for this vector here, so here you can see I'm taking each vector and making it a column vector for this matrix. Then if I take this determinant, I can take it by submatrices, which is what is done here. Namely, I think here, what are we doing? Something like maybe expanding on the first column and noticing that there's a lot of zeros to be done in the little sub matrices there. So we just basically get -1 times the submatrix that's left over. And that gives us a determinant of 2. Now, 2 is not 0. That means that this is an invertible matrix, which means going back to theorem 2 from the previous slide, we know that these columns have to be linearly independent. That's where we get to use this information. So these are linearly independent. Now, here's the deal. 4 vectors in R3 are linearly dependent. Thus, you have to say that v1 through v4 are linearly dependent. It's v4 that is adding in this little dependence relationship. And if we wanted to go through that, we could actually find out what those are. But since we have the fact that the dimension is not big enough to fit in 4 vectors, we know that there is a linear dependence relationship between these 4 vectors. Let's keep going and talk about the 2x2 matrix vector space here. And let's see if we can determine whether the following matrices are linearly independent in the space of 2x2 matrices. Now let's check something real quick. We had a dimension of the vector space here, or at least we know that it's at most 4, right? In fact, I think we know that it's exactly 4, but we can go through and prove that once we talk about basis here. Here we have 3 matrices. So 3 is less than 4. We know that we still can get linear independence from these 3 matrices here. Let's see if we can show that by calculating, starting from the matrix A, which is -1, 1, -1, 0. Let's calculate a squared and a cubed and see if this collection of 3 matrices, a squared, and a cubed, let's see if they are linearly independent. So I go through and calculate what a squared and a cubed are, and that's where they are. But now we want to see if we can solve this equation. R1a plus R2a squared plus R3a cubed. Is this equal to the 0 vector in the space of matrices? So again, we are looking at the 0 matrix. That's our big O, our capital O that we have right there. Well, each entry gives us an equation. The top left has to be equal, top right, bottom left, bottom right, and that gives us this matrix equation here. I'm just setting all the top lefts equal to 0, top rights, bottom lefts, bottom rights. I get a system of equations here. And it turns out, by the way, that there is a free variable in this system of equations. Well, what do we know if there's a free variable? Notably, when we do a row echelon form on this, there is a column where there is not a pivot element, namely this one right here. And so hence, we know that the system has a non-zero solution so that the matrices are linearly dependent. That's us using that theorem again, theorem 1 this time, to kind of help us out there. Now, to get to see this relationship here, we can ask, what is this linear dependence relationship? Here, we can actually go through and find it pretty nicely. A plus a squared plus a cubed is the zero matrix. You can see this adding each of these entries here. But this is a way for us to prove this if we don't even get to see what the matrices themselves are. We could go through and plug in numbers all day, but at the end of the day, usually it is much faster to go through and try and solve a system of equations here. Let's go ahead and see it in maybe like one of these other setups here. Let's see it with this collection of functions, e to the x, e to the 2x, and e to the 3x. Let's see if this is linearly independent in the collection of smooth functions over R. So what we're asking is, are these three functions, is there a way to write one as a linear combination of the other, essentially? If not, then they are linearly independent. So let's try and solve our linear dependence relation. Let's try and take constants a, b, and c where all of these things are equal to 0. Now, here's the deal. This is a neat little trick here. We could go through and say, okay, this is just a way to solve for what each of these a, b, and c need to be in order this is equal to 0. But I have three unknowns, a, b, and c. Right? X isn't technically an unknown. We want these to be for any x. So x is an unknown that we're trying to solve. However, I only have one equation, so I need to find a way to get two more. Well, if this equation is equal to 0, you know what else is true? If you took the derivatives of each side, then you would also have to have that equals 0 because you're just taking derivatives. Well, that's interesting for us because the derivatives give us unique equations. It's not just like 2 times the same equation, because e to the 2x, thanks to the power rule, it's going to give us a 2 out in front. E to the 3x, thanks to the power rule, it's going to give us a 3 out in the front. It's going to do the same thing if we took the derivative again. This time we get 4 and 9 in front of the e to the 2x and e to the 3x terms, respectively. And that's going to be 3 different equations for us to go through and solve. Let's see if we can try and solve this coefficient matrix. Here you can see what we have is e to the x, e to the 2x, e to the 3x, basically each of these terms. And here we're writing a, b, and c. The idea is that we're writing this as a system of equation or a matrix equation here. A is our coefficient matrix, which contains the functions themselves together with the coefficients that are in front of them, but without the things that we're solving for, this vector v, a, b, and c. If we get vector v to be something non-zero when we try and solve this equation, or if we get a free variable in here somewhere, then we know that what we're looking at is indeed something that is a linear dependence relation between these vectors. So we go through and do the solution stuff. I'll let you kind of go through and take a look at this. This is how we go through and say, how do we make this work? One way to try and see if this works, we have a square matrix A, so we can ask, can we take the determinant of this? Well, it can. It's going to take a little bit of time, but I think we can do it, especially since we can just multiply each of these columns. We can bring them outside. So we can just bring them out a little bit like here, because each of the columns have something in common, e to the 3x. So I can just say the determinant of this is e to the 3x times the original matrix, but this time without the e to the 3x in that third column. I can do the same thing with e to the 2x, e to the x, and get a big coefficient term out in the front, e to the 6x. Now we're just left with something that we can hopefully very easily take the determinant of. Once we do some row reduction, we can get something that's a little bit easier to take the determinant of, and we get a function 2 times e to the 6x, which is not equal to 0 ubiquitously throughout all x. Since this matrix is indeed invertible, we get that there is the only way that we can get a solution to the system is the trivial solution, because this told us, because a of x is invertible, that the solution is unique. And so because of this, the one solution that we know of, the 0 solution, is the only one. That is linear independence. And so A, B, and C must each equal to 0. Let's go ahead and see this generalized a little bit. This is a notion of what we're calling the Wronskian of a collection of functions. We're going to be using this, especially near the end of our course, talking about differential equations, because this is a tool that is useful for us in solving certain things. But we can also talk about it in terms of finding a linear dependence relationship between vectors in a functional vector space. So here we have n vectors these being functions, smooth functions on our interval. We ask them to be smooth so that we can take as many derivatives as we would like. And then what we do in finding this Wronskian is we take each of the functions in this first row and we just put them there. And then we put the first derivatives in the second row. This is a direct analog to what we had in our previous slide. And then we end it with the n-1th derivative at the very bottom here. The n-1th derivative happens in the very column row, and that is for each of the vectors that we have. Notice that this is a square matrix on purpose so that we can go through and essentially do the same stuff as what we did up above to determine whether or not there's a linear dependence relationship. Basically see if there is a determinant and see if it is non-zero. In fact, that is going to connect to our theorem. If this Wronskian is itself non-zero when I go through and take this determinant, notice determinant here, we have our determinant bars, for some x naught inside of AB, that means that this is not the zero function. Hence, the functions f1 through fn are linearly independent inside of C infinity. Notice, by the way, we could plug in any x naught that we would want because all we're trying to say is that this Wronskian is not the zero, or is not giving us the zero vector. The zero vector in this case being the zero function. The way that you show something's not a zero function is you just plug in some point and say that that's not equal to zero. This can be kind of a neat way to kind of get around this. If you get to the determinant and you're like, I'm not sure if this is a zero function or not, you can just plug in a point. If that point is not zero, hence you don't have the zero function here, and hence the functions are linearly independent when you go through and do this. But that's going to finish it up for just today. We've talked a little bit about span and linear independence, and we're still kind of trying to figure out the connection between these two things, at least from our more abstract kind of form. And that's what we're going to be talking about very soon, is this notion of basis and dimension inside of a vector space. But that will do it for us today. Thank you so much. Have a wonderful day.